Now let's apply what we learned in stationary functional approach to derive the finite element equations for a beam in bending. Remember that from the equilibrium of stress and external applied load in a beam, we found that the beam, the stress of a beam is given as the EI times the second derivative of the deflection. The second derivative of the deflection actually is a representative of the strain. It's actually second derivative times z, of course. Anyway, details of the derivation of the equilibrium equations for a beam can be found in other lectures. What I'm interested in here is that the stress times strain term will be replaced by the modulus of elasticity times the second moment of area multiplied by the second derivative of the deflection, d2w by dx2. So we end up again, like the last time, with d2w by dx2 all squared minus the deflection multiplied by the externally applied force, and this is the total energy. Applying the variation, so the variation will differentiate this term with respect to w, giving us 2, which eliminates the half of d2w by dx2 multiplied by the variation of the second derivative. The mathematicians who taught us the variation method said that the derivative of the variation of the derivative is the derivative of the variation. So we simply take the variation symbol inside the derivative to get the second derivative of the variation of w multiplied by the second derivative of w. Now what we have here is the variation of the total energy of a beam in bending. If we perform the integration by parts on this term twice, we will get the the boundary terms. I'm not going to go through that here, but we end up with the second derivative, the modulus of elasticity multiplied by the second moment of area, and we replace w and the variation of w by the shape functions that we have here. As you can see, this will actually give us the exact bending stiffness matrix that we got before using the weighted residual methods. So you end up with the element equation, stiffness times deflection equals generalized force, where the stiffness matrix is EI nxx, which is the second derivative of the shape function with respect to x. This is the column vector multiplied by row vector, so you get a 4x4 matrix here if you're using 2 node elements, and the generalized force term on the right hand side. So to conclude, we were able to derive the differential equations governing the mechanics of an elastic body, including the boundary conditions, starting from the total energy expression. That's actually the power of the variational methods. If you can write down an expression for the total energy, you can get everything from there. You can get the boundary conditions, you can get the differential equation, you can get the weak form, which we are interested in when handling finite element models. So everything is there when you're talking about energy. Just take the variation and there you are. Few steps and you get the whole thing. Also, we use that the what we call the weak form to derive the finite element model, and we found out that the model we got from the weak form or from the stationary functional approach was exactly the same model that we got from weighted residual methods. So it's the same finite element model. We approach it from two different directions, but we get the same thing. If you have the differential equation, start with weighted residual methods. If you don't have the differential equation, or if the model of modeling the differential equation is too difficult, start with the energy. You can always write an energy term, and you can always work with an energy term. You end up with the same finite element model.